inverse functions represents two functions you have the exact opposite order. More precisely, an inverse order of operations undoes whatever a set of instructions or operations does. For example, let's say I give you a written set of instructions. Okay, walk 10 feet forward. Step 1. Turn left. Step 2. Walk 8 feet forward. Is step 3. Step 4. Turn right. And step 5. Oops, missed an L there. Walk 6 feet forward. So here's a set of instructions. You're going to walk 10 feet forward, turn left, walk 8 feet forward, turn right, walk 6 feet forward. An inverse set of operations is going to be the exact opposite procedure. So the first thing I'd like to look at is maybe a graphical picture of this. Let's say you are standing at this point here and you're facing in this direction to begin with. Now, according to my operation, I want you to walk 10 feet forward. If each one of these little hash marks is a foot, then your path will be walking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you will end up at this point. The next set of instructions was to turn left. Now, you're still facing this direction right now. So when you turn left, you're now going to end up facing this direction. Next set of instructions is to walk 8 feet forward. So we will 1, 2, 3, 4, 5, 6, 7, 8. Tilt that up a little bit. And last but not least, you are asked to turn right. Well, first of all, right now, when you get there, you're facing this direction. When you turn right, you will be facing this direction. Last but not least, you are asked to walk forward 6 feet. 1, 2, 3, 4, 5, 6. And you finish in this position here, facing this direction. It's your final location. Now we're going to talk about how to take you exactly backwards to where you were. Okay, so you're facing forward right now in this direction, and I want to first of all take you back to this position, still facing the same way the whole time. So, first set of steps would be go back 6 steps, or 6 feet. So if you do that, you're going to take this path, you will end up here, and you're still facing in the same direction. So I've taken you back to this position. I now want you to change direction so you're facing this way, which would mean that you would have to turn left.
Oh, well, he turned.
Now you're facing this direction. I want you to get back down to this position, facing the same direction the whole way, which means you will have to go back 8 feet. So now you're traveling down here. You end up at this position still facing this direction. But I need you to now turn to face that direction, which will be turn right. Now you're facing in that direction. And last but not least, you will go back 10 steps, or 10 feet. And you'll end up following this path, ending up at this spot, facing the same direction as when you started. This is an example of an inverse set of instructions. Notice, in the very first set of instructions, we started at point A. That was our beginning point. When we were done, we ended up over here at point B. So this is our beginning, this is our end. But the second set of instructions here begins at point B and took us back to point A. Whenever we're looking at an inverse, whatever the original function does, the inverse is going to undo that set of operations. Let's look at some other examples. Let's call this a factory that builds cars, and this a garage. Now, let's say you have some parts. And they go into the factory, so this is in. And out of the factory comes a pickup truck. And your pickup truck happens to be parked in the wrong location and gets stolen. That pickup truck is driven into a special kind of garage called a chop shop. When that chop shop gets through with your pickup truck, what's going to come out? Some parts. Those parts could be shipped somewhere else and taken into a factory, and out of the factory can come out your pickup truck. We can go round and round and round with this procedure. These two functions are inverses of each other. Whatever one does, the other undoes it. Now, let's look at a mathematical inverse. So let's say F and G are both mathematical operations. And I take a 2 and I plug it in to F. And I don't exactly know what the function does, but whatever it does, out of that function, we'll say, comes a 6. If G is in fact the inverse, the opposite set of operations, Then when I take that 6 and I plug it in to the G operation, out's going to come a 2. And I could have started it at G. Start with a 6 at G, out comes a 2, take it into F, it's going to take it right back to the 6. It makes a loop. One function takes it halfway, the other one brings it right back around. So this is the general idea of a function and its inverse. Now, I'm going to give a definition of a function and its inverse based on this logic. It has 2 pieces to my definition, but it has the exact same principle. Step 1, I'm going to start this time with G, doesn't matter where we start. And I'm going to take X and I'm going to plug it in to G. And out of G is going to come this amount. This symbol literally says the output of G when you plug in X. We learned what that symbol means before. So it's very important that we have the literacy part of it. Out is coming G when we plugged in X. I'm going to take that output and I'm going to take it to the other function. And when I take that in to the other function, I am expecting to get out whatever I started with. In this case, I started with X. So, part 1 of my definition. Let me read this to you. When I take the output G of X and I plug it in to F of X, if these functions are inverses of each other, F will put out X. All about literacy, being able to see in the symbols what we see in the chart. So again, in goes X into G. G produces an output, step 2. Take that output, plug it into F. F will take it right back to where we begin. The other way that we can look at this procedure, take an input into F of X. What's going to come out of F of X? I don't know, but this is the symbol that represents what comes out of F of X. That symbol literally reads the output of F for the input X. Then I'm going to take that output, and if G is an inverse, it must undo whatever F did and take it right back to X. Completes the loop. Second part of my definition of an inverse, F and G are inverses of each other. If I take the function G and I plug in the output from F of X, G is going to take it back to X. So this is my definition of an inverse relationship. And I can now say that G of X is the inverse of F of X. Now, one of the things you should understand about mathematicians, we don't like to write sentences. We prefer to use hieroglyphics instead of sentences. We like to write with pictures and symbols. So I'm going to take the sentence, G is the inverse of F, and I'm going to write that with symbols. New notation. The function G of X is in fact the inverse of F of X. Notice this symbol down here that is not representing a -1 exponent. This is a picture that represents a sentence. And that -1 part of the picture tells me that there's a relationship directly back to the function f. These two functions are inverses of each other, stated right with my new notation. Okay, I'm giving you a function f of x in a form of a table. We're going to find the inverse of f of x from that table. We're going to use the idea of what an inverse is fundamentally. Notice, f of x takes a 2 and makes it into a 6. The inverse should be able to take that 6 in and output a 2. The function inputs a 3 and outputs a 4. The inverse will input that 4 and output the 3, undoing it one at a time. Inputs a 4, outputs a 5. This one's going to input that 5 and take it right back to 4. Inputs 5, output is 3. The inverse will take that input and take it right back to the 5. Input a 6, output a 2. The inverse will take that output in and put it right back to the 6. This is my inverse of f of x. Notice, every x value on the original function becomes the y value of the inverse function. We're now going to look at a graph of a function, and we're going to find its inverse. An important thing to know about a graph of a function and its inverse, it's that the two functions will have the same basic shape. This is important to remember, because when I make a graph, we need points to make a graph, but it's important to know the basic shape of the graph. So if you know the basic shape of f of x, then you also know the basic shape of its inverse. It's just a matter of locating where that inverse is. So, first thing I'm going to need is some points from the graph f of x. I'm going to label these points. This is the point. Actually, I'm just going to make a table of these points. So, this is the point. This is f of x. 0 for x has a y value of -2. 1 for x has a y value of -1. 4 for x has a y value of 0. And maybe one more. 9 has a y value of 1. This is my function f of x, some points from the function f of x. Everyone okay with that? Now, I'm going to give you some points of the inverse. This is going to be the inverse of f of x. And I'm going to take that. F took 0 and made it a -2. The inverse is going to take it back to 0. Took a 1 and make it a -1. The inverse will take that -1 back to 1. F took 4 and made it a 0. The inverse will take that 0 back to 4. The function took a 9 and made it a 1. The inverse will take that 1 and make it back into a 9. I'm now going to graph these points. Negative 2, 0 is about there. Negative 1, 1 about there. 0, 4 here. And 1, 9 would be up there. We can't quite see it. But if I connect my dots, notice that this graph has the same basic shape as f of x. This is my graph of the inverse of f of x. Okay, we've done the inverse of a table, we've done the inverse of a graph, now we're going to do the inverse of a formula. The very first thing I'm going to do to this formula before I find its inverse is I'm going to rewrite this formula using standard notation. That is, instead of writing it as f of x, I'm going to write it as y. So it's still the exact same formula. I'm just taking out a function notation for a bit. Now I'm going to write the inverse. The most important thing is, what is an inverse? Fundamentally, the inverse function is going to have the output that's the same as the original function's input. The inverse will have input that is the output of the original function. So the inverse is going to look like this. There is my inverse function. Now, I'm going to take that function and I'm going to solve it for y because the format is not acceptable. So how do I solve this for y? I'm going to remove everything away from y. The very first thing I'm going to do is multiply both sides by 3. The next thing I'm going to do is remove the 7 by adding 7 to both sides. Oops, that's a 7 there, got ahead of myself. 7 equals the 2y. Next thing I'm going to do is divide both sides by 2. Last but not least, and this is possibly one of the most important aspects of it, I'm going to let everyone know that this is the inverse of f, the notation. This is a very important last step. So I have now found the inverse function of f of x.